Okay, last lecture on 2.1 on the derivative. Obviously, derivative carries through, but last lecture on 2.1. Just going to do a few examples of things that are pretty common. What would the derivative of 1 over the square root of x be? What would the derivative of 1 over the square root of x? Well, I know the definition of the derivative, and that obviously is the whole point of this section, right? H. That's the definition of the derivative, right? So if that's f of x, then this is f of x plus h. So I just put that into the definition. And then what this becomes isn't the definition anymore, plus h minus 1 over x over h. That's the derivative, that's the definition of the generic derivative. This is the definition of that derivative. And they got to work that out. Well, how do you add or subtract fractions? You need a common denominator, right? So what I'm going to do here is I'm going to multiply this side by 1 over root x. Oh, sorry, root x over root x, sorry. Multiply this over root x, and then this side by square root of x plus 1 over this x plus h. So, anytime like any fraction, right? 1/3 minus 1/4, you can multiply top and bottom by 4, top and bottom by 3, you get 12, right? Same thing here. I'm going to multiply this top and bottom by that. So, what do I get when I work that out? I get root x minus plus h all over h times root x, and this is all over h. Oh, and I forgot my limit thingy. And then we know we have to multiply by the conjugate pair, right? To get rid of the square root. Square root of x plus x plus h plus. So when I FOIL that out, first times first, x. The whole point of multiplying by the conjugate pair is those go away, and then last times last. Now be careful here. All over, wow, this is getting big here. Plus h square root of x, square root of x plus the square root of x plus h. And now this is all over h. Now I know I could bring the h up here, but I'm just being silly and leaving it down there for right now. So note, now be careful here. The x's cancel, but that negative is attached there. So I get negative h over the square root of x plus times the square root of x times the square root of x plus the square root of x plus h. Now watch a little trick here. It's all over h, but wait a minute. Dividing by a number is the same as multiplying by its reciprocal. It'll make it easier to see, in my opinion. Dividing by h is the same as multiplying by 1 over h, right? Dividing by a half, or dividing by 2 is the same as multiplying by a half, right? So then I cancel these out. Oh, I forgot my limit thingy. Don't worry on your homework or test if you forget the limit thingy. I'm not going to get all upset, but some teachers in college will, so just be aware of that. Okay, so what do I get? Negative 1 over the square root of x plus h times the square root of x, and then parentheses, square root of x plus h. Now the h's are going to 0. Right, h is going to 0, so you get the square root of x times the square root of x, square root of x plus the square root of x. Now do the math right on this. The square root of x times the square root of x is, oh, don't forget that negative, is x and then 2 root x. So negative 1 over 2x root x. And if you want to be fancy, you can write it as negative 1/2 x to negative 3/2. Now, like I said, notice that there's this immense amount of algebra in this section. When we get to 2.3, we're going to start learning some shortcuts. But for right now, this is kind of how we do that. Okay, let's look at a couple of graphical ones. Okay, so next question. Suppose that's the function f of x. Suppose this is the graph of f of x. What would the derivative be? It's going to be a little weird, but it's not hard. Okay, the derivative is the slope, right, of this straight line. Over 1 up 3, so the slope of that line is 3. So that means the derivative is 3. Notice the tangent lines are going to be 3 here the whole time. So from 0 to 1, it's going to be 3. Now, whenever it's pointy, you don't want to count it because that derivative here is 3, but here the derivative is going to be 0. Okay? So the derivative here is going to be 0. And it's going to be 0 from 1 to 3. Now again, it's pointy there. Whenever there's a pointiness to it, there's no derivative. Why? Because the derivative from the left isn't the same as the derivative from the right. It's kind of like the lemon idea. Here the derivative is 3, here the derivative is 0, so nobody gets that point. Nobody gets it. When it's pointy, nobody gets it. That's, we just decided. Okay, here, if that derivative is 0, and then I got to figure out what that is. Over 3 down 3. Okay, so this derivative was 0, and this derivative is negative 1. So. Now, notice the graph looks funky, right? Why does it look funky like that? Because of the straight lines, right? We'll do one that's not straight in a second. A straight line has a constant for a slope, and constants graphs look like that, like y equals 3, or y equals 0, or y equals negative 1, right? So notice the derivative does look kind of funky, but it's certainly a lot easier to do than the analytical one, right? Okay, this is what we're going to be doing next. Okay, the lecture tomorrow, I'm going to do a lot more of these. So don't panic if you're like, this one's hard. It's not hard. It's just different, and there's a couple questions like this in 2.1, but all of 2.2 is on this idea. Okay. So you can think of this as a transition question. You kind of have some questions like this on 2.1, but there's a lot of questions like this in 2.2. So the lecture for Friday will be but I'll do a bunch of examples like this. Okay. Okay. So how am I going to graph the derivative here? This is not exact like the other two were. Okay. This is kind of a little more touchy-feely. So what you first do, there's 3 things you're looking for, okay? First is, when is the derivative going to be 0? Those will help you a lot, okay? So the derivative will be 0 here, and the derivative will be 0 here. So one thing you can do is you can drop those down onto the graph here. Now, you don't have to put the dotted lines, that's just me. I think it's a good idea, though. Okay. So I know the derivatives are, now, this is where it gets a little bit touchy-feely, right? There's a couple things we're going to do here. They're intellectual, by no doubt. They're definitely very thoughtful things we're doing. But it's not like you can just grind it out. You actually have to think about it, okay? It's not hard, like like that. You don't have to think about that. You just kind of, get some thinking, but basically you're just doing a bunch of algebra, right? You're just following the frickin' rules you learn. You're not really actually thinking about it. This one you got to think about a little bit. What we notice here, from here to here, the function is going up. This is going to be important. It's like a calculus 101. If a function's going up, or we say the function's increasing, if a function's increasing, we say its derivative is positive, right? Because if it's going up, that means that the derivative has to be positive, okay? What does that mean? It's got to be here somewhere, doesn't it? It's got to be, right? It's got to be there somewhere, okay? Then here, notice that from here to here, from that 0 to this 0, where the slope is 0 or the derivative is 0, is negative. So the graph has to be down here somewhere. I don't know where yet, and we'll figure it out, don't panic. And then from here to here is positive. Now again, make sure you get what I'm saying here. Since the function is going up, we say the derivative has to be a positive number. So the graph has to be here. It's got to be a positive number. Here, the derivative is going down. So it's got to be what's called a negative number, okay? And then, here, the derivative from here to here, if I take any point there and find any derivative, since the function is going up, we say the derivative is positive. So the graph has to be there. Now, just for the sake of discussion, let's assume this is a sine wave like we think it is. And I'm going to add this part here, but let me put it in green because I don't want to, I'll leave it blue. But we're not going to graph that part. But I put it there for a reason. So let's continue on here. Okay, so, and maybe we will graph it in a second. Now, the next idea, and this is a really important idea, is we're looking for what are called inflection points. Watch what happens here. The derivative is now I'm going to explain it one way, and then I'm going to answer. We're going to come up with a way to find them quickly. Notice the derivative is 0 here, and becomes more and more and more negative till about here, and then back to being positive. So that point right there is the most negative it's going to be. We know it's negative, but the most negative, and I don't care where you put that point, but once you drop it, it's got to be the most negative. Now, let me show you a shortcut way to find that point. This is called concave down. This is called concave up. When it switches from concave up to concave down, that's where it's going to be at its most. Same thing here. Notice the derivatives are positive, 0, and the derivatives are positive, so the most positive there. Okay. And then over here, 0, and then the most positive here, because then it goes back, because the slopes go back to 0 again, so the most positive there, don't they? So when you graph the actual derivative then, just connect the dots and just try to do it as fluidly as possible. Now this is the most positive, it's going to kind of turn around after that, but let's not worry about that. So notice that if you have a function, we can graph its derivative, okay? Now, don't panic if this seems a little tough. I'm going to do a whole bunch of them on the next video for Friday, okay? And this is actually more for 2.2, but there's a couple questions like it in 2.1, so I figured I would throw it in. Okay.